Hello, we are here to discuss parameter estimation, and we will begin with an example. Suppose we have a random sample with 3 observations from a Poisson distribution, and we can see our observations here, 4, 7, and 2. Now, the joint probability mass function, well, this is a random sample, and so the marginal distributions are independent, and this joint probability mass function splits into a product. And so we have, well, exactly as we see here, using properties of exponents, we can write this as lambda to the 13 divided by 4 factorial, 7 factorial, 2 factorial, and then e to the minus 3 lambda. Now note here that lambda is some positive number, and this is our parameter. Now, we are used to knowing the parameters of a distribution. Namely, we would specify which particular Poisson distribution we are working with, and then we would evaluate a probability. However, here, the parameter lambda is unknown. Moreover, well, we want the lambda. So we want the parameter lambda with, well, this as likely as possible. So we could say f of 4, 7, 2, lambda as high as possible. Well, let's just evaluate. If we evaluate at lambda equals 1, f of 4, 7, 2, and lambda equals 1, we will have 1 over 4 factorial, 7 factorial, 2 factorial, and then e to the minus 3. And this is, well, we could use R. We could also use a calculator. 1, 2, 3, 4, 5, 6, and then followed by 206. For lambda equals 3, here we get 3 to the 13 over this 4 factorial, 7 factorial, 2 factorial, and then e to the minus 9. And this is approximately, well, here we only have 3 zeros, so 0.000813. Well, it seems just by testing lambda equals 1 and lambda equals 3, it seems that our random sample, the data, is more likely with parameter 3 than parameter 1, because this number is bigger than this one. Some terminology here. So we haven't finished this problem. It was just the beginning of an example, but terminology for statistical inference. This function is called a likelihood function. And here, x1, x2, x3 are known, and the lambda is the variable. Estimating this unknown parameter by maximizing this function is called maximum likelihood estimation. All right, now we'd like to continue our example and maximize this likelihood function. However, before I get started, let's look at a picture. What we're looking at is our likelihood function. Here, I've entered this as a function of x, but we have, think of this as f of lambda. Now, the window that I have chosen to plot this function, we can very clearly see a maximum. In fact, Desmos tells us happens at lambda equals 4.333. Look at the y-axis. Do you see how small these numbers are? So 0, 0, 0, 5, 0, 0, 1, 0, 0, 1, 5. This is a very, very small y-axis. If we looked at this graph on maybe how we would normally plot. So we know probabilities is going to be between 0 and 1. So let's change this to where now y goes up to 1. It is very hard to see really anything from this graph. So the y-axis is very, very tiny. Now, think about using R to maximize, which we will. If you have a whole lot of very, 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 very small numbers multiplied together, we can get errors trying to maximize the function as is. So I have zoom out, and we will maximize what is in blue, the log of the likelihood function. You notice the maximum occurs at the exact same x value. Of course, this will happen because the logarithm is an increasing function. But in R, with numerical optimization, you will see fewer errors working with the log likelihood function. Moreover, by hand. So we will do this analytically in just a moment. Applying the logarithm will help us. We have a lot of products and powers here, and we can simplify when we're going to take derivatives by applying the logarithm. We will maximize the log of this likelihood function, and I will call that L of lambda. Really, I'm thinking about natural log here because I'm going to be using derivatives, and the natural log, well, it's the easiest to differentiate. So let's take the natural log of all of this. We have lambda to the 13 divided by 4 factorial, 7 factorial, 2 factorial, and then e to the minus 3 lambda. Well, some wonderful things happen here. We have to go back and remember our log properties. First thing you notice is I have a product here and here. This will turn to a sum of logs. So let's do that first. We have ln of lambda to the 13 divided by 4 factorial, 7 factorial, 2 factorial, and then plus natural log of e to the minus 3 lambda. We keep going with our log properties. Now, here, technically it would be 2 steps. I have a quotient, and then in this numerator, I have a power, but I might just write it in 1 step. So we will have 13 ln of lambda minus ln of 4 factorial, 7 factorial, 2 factorial. And then this part's very nice. Natural log of e to a power is just the power. So we have minus 3 lambda. Okay, here's my log likelihood function. Well, how do we maximize? Calculus 1, we can take the derivative, set it equal to 0. And really, we already observed that we have a maximum here. So let's take the derivative with respect to lambda. Here I'll get 13 over lambda. This part is just a constant. And then I have minus 3. Well, L prime of lambda equals 0. This would give me that 13 over lambda equals 3. And solving for lambda, well, 3 lambda would equal 13, or lambda will be 13 over 3. Now, typically, for the maximum likelihood estimator, we put a little hat on it. So here is our maximum likelihood estimate for this parameter, lambda. We have solved. This is 4.3333 repeating, and that is what we saw when we looked in Desmos at a graph of either the likelihood function or the log likelihood function. So it's nice to have verified this using calculus. That was an example and a fantastic one, but I would like to speak generally. So suppose we have a random sample, x1 through xn, from a Poisson distribution, and we're trying to find this maximum likelihood estimator, lambda hat. Well, the likelihood function, f of x1 to xn, lambda to the x1 divided by x1 factorial, e to the minus lambda, out to lambda to the xn over xn factorial, and then e to the minus lambda. Well, just as we did before, we can use properties of exponents. First of all, there should be a 1 here. Now, my numerator will be lambda to the sum, I equals 1 to n of xi. We have e to the minus n lambda. Then in the denominator, I have a product of all of these factorials. So we have a product, I equals 1 to n of xi factorial. Well, this looks intricate, but the good news is, well, we did an example first. Now let's look at the log likelihood function, which we will try to maximize. Well, you see, very much like we had in our example, maybe I'll go ahead and split this because here we have this times this. So I will go ahead and write that as a sum of natural logs. We have the natural log of, I'll just copy this entire thing and paste, and then plus the natural log of e to the minus n lambda. Well, we take the exact same simplification step that we did in the last problem. This will really be two things happening at once, but we will have a sum, I equals 1 to n of xi, and then times natural log lambda, subtract off the natural log of the product, I equals 1 to n xi factorial. And then the second term, it's a minus. We just have a minus n lambda. I mean, technically you could break this into more logs, but you notice there is no lambda in this. So with respect to lambda, this is a constant, and so I'll just leave it like this. Okay, let's take the derivative with respect to lambda. Here, we have ln lambda. The derivative is 1 over lambda. So I'm going to have 1 over lambda times this sum, and then minus the derivative of n lambda with respect to lambda is just n. When we set this equal to 0, this is where we see something really cool. You notice we will have that lambda will equal 1 over n times the sum, I equals 1 to n of xi. What is this? Well, this is just the sample mean. So we get that our MLE estimator, lambda hat, is just the sample mean, x bar. When we're working with Poisson random variables. Now, you can go back and check here. We have these 3 observations. We can see them here, 4, 7, 2. What is their mean? Well, take 4 plus 7 plus 2, 13, divided by 3. It's exactly this. Next, let's move into a random sample from the normal distribution. And you'll notice it says here, analytic MLE. What does this mean? Well, it means we will be using calculus, just as we did in the first example. You will see in our Canvas course some pages where you can use R for numerical maximization of the likelihood or log likelihood function, but we are using calculus in this lecture video. Very nice. Okay, so we have x1 through xn, random sample from the normal distribution. Now notice we have 2 parameters here, the mean mu, standard deviation sigma. And our likelihood function, well, once again, we can write it as a product of the marginal PDFs. And so that's what this is. Okay, well, we can use properties of exponents very similar to as we did before to simplify this. You notice I have this 1 coefficient out in front. I have 1 over the square root of 2 pi times sigma, and this is all to the n. And then I have e to the minus 1 over 2 sigma squared. But then we have a sum where I equals 1 to n. We have xi minus the mean squared. For the log likelihood function, well, maybe I'll take an initial step. Here I have a product of 1, 2 things, and so I can write that as a sum of 2 logs, where this first one, you notice this 1 over to the n is really square root 2 pi times sigma to the minus n. Okay, so we have square root 2 pi times sigma to the minus n. And then we have ln of, well, all of this. We keep going with our log properties. Maybe I'll rearrange things. So let's do this one first. This is ln of e to something, and so we just get minus 1 over 2 sigma squared. And then we have this sum. We have xi minus mu squared. Now we can bring this constant out in front. Will be minus n. But I can also break this into a sum once I do that. So I'm going to do 2 steps at once. We will have minus n times ln square root 2 pi, and then minus n times ln of sigma. Why do I want to do that? Well, I'm about to, as you can see, take the partial derivative of this L with respect to mu, the partial derivative of this L with respect to sigma. And the good news is this term is a constant for both of those, really. So this is as far as I'm going to simplify this log likelihood function. Partial derivative of L with respect to mu. Well, where's my only place I see a mu? So with respect to mu, constant, and I just have here. Now you notice I can differentiate term by term. So this is a sum, I equals 1 to n. If I differentiate term by term, well, I just bring down this power, which is 2, and then times the derivative of the inside function, which is minus 1. And so I get the following. Positive 1 over sigma squared times the sum, I equals 1 to n of xi minus mu. We can simplify this here, so I'm going to keep this out in front. We add I equals 1 to n xi, but then this part, we add I equals 1 to n mu, it's just here. So minus mu times n, okay? Now, take the partial derivative of L with respect to sigma. Here we have sigma in multiple terms. So now this part is a constant. When I differentiate minus 1/2 sigma to the minus 2, well, I'm going to bring down the power to the power minus 1. It's just power rule. And I will get positive, oh, write it down, positive 1 over sigma cubed. And then we still have this sum. This is the constant. Okay, now differentiate this part. We get minus n over sigma. Maybe I will simplify this one as well. We can factor out as 1 over sigma cubed from both terms. This part remains the same, and then we have minus n sigma squared. Okay. So let me underline. Here's one partial derivative. Here's another partial derivative. I have simplified both of those. Now I want to set both of these to 0. So partial L with respect to mu equals 0. What do we get? We just set this part to 0. So 1 over sigma squared is never 0. And you notice we get mu. Ah, how great is that? We get that mu is the sum I equals 1 to n of xi, and then divide this by n. So this MLE estimator, when you're working with normal observations, is just the sample mean. Now, take the partial derivative of L with respect to sigma, set this equal to 0. And what do we get? Well, this part must be 0, so we get that sigma squared is 1 over n times the sum I equals 1 to n of xi minus mu squared. Well, to get our MLE estimate for the standard deviation, first of all, you can take a square root. So we have 1 over n times the sum I equals 1 to n. But then we would use, instead of mu here, we would use this MLE estimate. So we would have xi minus the sample mean squared. Now, this is wonderful. We have very nice formulas that we actually took a lot of work to get. A lot of calculus here, but it's important to understand that these are special for the normal distribution, and you might not always have the maximum likelihood estimators work out exactly like this. All right, my next question, how else can we estimate parameters of a distribution? And the answer, we can use what's called method of moments, and this uses the sample parameters directly. So suppose we have a random sample, x1 through xn, and we're thinking about this as sampling from some population, and the population follows some distribution that we don't know. But the first moment of the population is the mean, expected value of x. Well, we estimate this using the sample mean, x bar, which is a sum. Oh, I need the 1 over n. And then we add up, say I equals 1 to n of xi. And in R, we can calculate using mean, as we have done already. Now, the second moment of the population is the variance. And we can estimate, as you can imagine, using the sample variance. So what is the sample variance? Well, in R, we have used this command. However, as a formula, the sample variance is typically referred to as s squared. We have a 1 over n minus 1. And then you add up I equals 1 to n of xi minus the mean squared. Now I'd like to make a remark. So it's kind of interesting. For normal observations, you see we had this MLE estimator for the standard deviation, which we can just go back, copy and paste. But you notice what we see in this formula. It has a 1 over n. Okay. Versus if you look at the method of moments estimator or the standard deviation, you see we would take a square root of this, and it has a n minus 1. So they're not the same. For large n, they're going to be very close, but they are different. And that was a remark I wanted to make. Maybe in closing, I will mention some method of moments estimators for the chi-square distribution and the exponential distribution. Both of these distributions have only one parameter. Chi-square, we have k degrees of freedom. Exponential distribution, we have one parameter, lambda. However, Well, we have a different mean and different variance. They're two different numbers. So how would we go about a method of moment estimator for this one parameter? So typically, if x1 through xn is a random sample for a chi-square distribution, here we have k degrees of freedom. This is our one parameter. Population mean is k. And so we use the sample mean, which is our first moment. And similarly, if we have a random sample of size n from the exponential distribution, here we have one parameter, lambda, and we know the population mean is 1 over lambda. Our method of moments estimator for our parameter will be 1 over the sample mean, like this. We use the first moment in each of these cases. Well, this is the end of our lecture video on parameter estimation. Thank you so much.